It broke up like a year ago.
So,
No. I know there's any left.
alright,
Oh, I thought you
so
said
zeros of the function occur where the function has a value of 0. So if I gave you these three functions, number 1, f of x equals 2x plus 7. Number 2, g of x equals x squared minus 25. And number 3 is your you try in just a moment, f of x equals x divided by 3 plus 2. If we wanted to find the zeros of these functions, we want to know where the function has a value of 0. So what can I plug in for f of x? 0. Because I want it to equal 0. And then I just solve. So you'd move the 7 over. You divide by 2. And this is exactly what we did when we were doing our t-charts on our linear programming problems to find the x-intercepts, wasn't it? We'd plug in 0 for y. So that 1 0 of the function is negative 7/2. Or that is the only 0 of that function. Okay, let's take a look at our second function. G of x equals x squared minus 25. So if we want to find the zeros of this function, we rewrite it as 0 equals x squared minus 25. That tells us where this function, g of x, has a value of 0. We substituted it in for g of x. So we'll solve this. Obviously, move the 25 over. All right, now we have this equation. 25 equals x squared. How do we undo a square? Take the square root. When you take the square root, you get the positive and the negative. So it's plus or minus 5. So this function has two zeros. One occurs at positive 5 and one occurs at negative 5. And we talked about these zeros of the function are located at the x-intercepts. So if I graph this one, you would know it would look like, well, I made that a little too close. Hold on. And I graphed it in the totally wrong place. 1, 2, 3.5. So it would be right here. If this were 7. Okay, so do you see that this crosses the x-axis at negative 3.5? There's its 0. The function has a value of 0.
I thought it was 5.
Yeah, wouldn't it be 5?
This one's this one. And now let's do this one. This is a function that we're going to study in depth next year. It's called a quadratic function. And this one happens to have a y-intercept way down here at negative 25. And then it crosses the x-axis at positive 5 and negative 5. And so it would cross twice. And it has two zeros. Oh, I totally missed. See if I can hit that one better. All right. We'll make it a really big tick mark. Okay? So this is where the zeros of the function occur. And when we use our technology, we can find zeros on the calculators too.
Oh, yes.
Okay, you try number 3. Please find the 0 or zeros of this function.
6. Oh, wow. Maybe 6. Maybe just give you 7.
You plug in x. We plug in 0 for x.
Negative 6.
See where I plug in 0 here, and where I plug in 0 here. We're going to do the same thing here. We want to know where the function has a value of 0. Okay, so we'll move the 2, and we'll multiply by 3, and negative 6 equals x. Are we all happy? You good? Okay. Alright, so one of the zeros of this function is negative 6. So if I were to graph it, that would tell me it's going to cross the x-axis at negative 6, which gives me an x-intercept of negative 6, 0. Alright, so here's a picture of a graph. So we don't have to do it algebraically if we have a picture of the graph. Here's some crazy looking graph. Where does the function f, I labeled it function f, have a value of 0? So what are the zeros of this graph?
Negative 3, negative 1, and 3.
Beautiful. Negative 3, negative 1, and 3. So the zeros are negative 3, negative 1, and 3. So those are also my x-intercepts. But x-intercept is a point, so I'm going to write it like a point. And all our points, I'll definitely put in parentheses, so I'm showing that I know it's a point. Okay? Now on your last test, even though during the middle of the test I was grading 6 periods and I was getting frustrated because they weren't writing ordered pairs with parentheses around them, and I told y'all, remember during the test I said, if it's a point, please put it in parentheses. But I don't think all of us have enough practice with that because some of us still didn't do it on the test, even though I made that statement out loud during your test. All right, y-intercept right there in it. 0, 2. 0, 2. Any questions? All right, how would we find the intercepts algebraically? Okay, what do you think?
You would, yeah, I think you would want to move 2x to the other side.
That's one way we could do it. Remember, that's all we did when we graphed things on linear programming tests, isn't it? We found our x and y intercepts. So to find the x-intercept, we plug in 0 for y. Well, that's what we did to find the zeros, wasn't it? So 0 equals 2x minus 5. So we can move 5 over and get 2x. So we get 2.5 equals x. So our x-intercept is 2.5, or 5 halves. Now the y-intercept, all we have to do is plug in 0 for x. And we plug in 0 for x. What's 2 times 0? 0 minus 5 is negative 5. So this we've already been doing. So we know how to find the intercepts algebraically. We know how to look at a graph and find the intercepts. And the x-intercepts occur at the points where the function has a value of 0. So the x-intercepts and the zeros are kind of like the same thing. So far nothing really new, right? Okay. You try these. These are fun ones. Let's see what you can do. You may or may not be able to get both of them. But I gave you more interesting functions. Yes?
Why is the x in between
It's absolute value. It is absolute value.
the Yeah, why should it just be x?
No, but it has to be possible. It's because the second plug in x.
3 times the.
Times the absolute value of x.
It's 3 times
Divide
x.
divide.
Well, no, positive 7.
It's not big.
How would you try to remember? Ian.
We need to go to 3x to that first value bar to do the same thing.
The 3 inside the absolute value?
Well, if like times, if it was like, if x is negative 5, then it's 5 that's the value, then times 3 on the outside, that's 15. Then if 3x on the inside, then it's still the same thing. Because like negative 5 for the x times the 3 on the inside, and then it's absolute value 15. It's still the same thing.
Yeah. I see what you're saying.
Oh yeah, right there.
So the x
Wait,
is
that's
separate
easy.
from the
The number 2 is an imaginary
I want to
number.
make sure that
I just have to ask. Can you come look over there?
Oh,
yeah,
that's a
so 7/3.
I got negative
So you'll have
1/7.
absolute value.
Yeah,
So
that-
minus it's just 7/3
Yeah, I was like,
equals
it's-
x. It's just
Then
as
I-
negative. Wait, but
Negative 3. Absolute value. Oh, I figured out how to do 2. You guys have figured out how to
I had it on the
do
No.
I figured out how to do that. You just have to, instead of putting in the calculator square, you just do one of those.
I got it. Number 1 is done. Number 1 is weird.
It's dumb, but it's fine.
Okay.
I mean, it already is
Alright, number 1, if we're going to find the zeros of the function, the way we do it is plug in 0 here. So we have 0 equals 3 times the absolute value of x minus 7. We move the 7 over, we get 3 times the absolute value of x. We divide by the 3. Alright, now, this is true if x equals positive 7/3. If I plug positive 7/3 in there, does that make a true statement? Yes.
But if you put it
If you plug in negative 7/3 and take the absolute value of it, does it equal 7/3?
Yeah.
Okay, so guys, every time you get to this point, the absolute value of x equals some number. The answer is positive or negative n. Because if I put the positive in here and took the absolute value of it, it works. And I will put the negative in. Any number in the world. So if we had, okay, maybe not any number in the world, but the absolute value of x equals 8. So x equals plus or minus 8. If the absolute value of x equals, equals 4, then it's plus or minus 4. If it is negative, is this possible? No. There's no solution.
But why is there no solution?
Because I can't take the absolute value of anything and ever make it equal a negative number.
Whoa.
You guys have no idea about absolute value, and I have discovered that.
Yeah.
I have some.
Yeah, we only spent like a day on it
We
last
just have to
time.
like, oh well.
I have
Okay.
some.
Okay. Just I didn't think so. So our zeros are 7/3, negative 7/3. So the x-intercepts are 7/3 0, and negative 7/3 0. So this is if n is greater than 0. Okay. And our y-intercept, if I plugged in 0 for x, 0 times 3 is 0, minus 7 is negative 7. Nobody's shutting down. Come on, come back. If you plug in 0 for x, if I plug in 0 for x, what's 3 times 0? 0 minus 7 is negative 7.
Wait, there's no absolute value of 0. Nothing.
It's okay.
Are we supposed to? Yeah, I'll just.
That's fine.
Later. So, but I thought it was x is equal to plus or minus.
I remember plug
Plus or minus a number. So like, I had negative 7 over 3 as my x-intercept, but you said x is equal to plus or minus a number. I guess that is a number.
I said, yeah, 7/3 and negative 7/3 are numbers.
So, but except that means couldn't like the x-intercept be like 10?
Sure.
Okay, so
But not in this case.
Okay.
Alright, this one. So we say 0 equals x cubed plus 27. So negative 27 equals x cubed. Now, most of you intuitively knew to take square root. If it's a squared, we take a squared root. So if it's a cube, we take a cubed root. So you're asking yourself, what number times itself 3 times is negative 27?
Nothing.
Yes. Negative 3.
Oh, yeah. 'cause
Negative 3 times negative 3 times negative 3 makes negative 27. So there is only one answer. One answer. We can take odd roots of negative numbers. We just can't take even roots of negative numbers and get out a real number. Yes, ma'am.
Kind of off topic, but what is that?
What's that?
Like that screen.
That's a
Oh, that is a projector screen. The teacher that taught in this room before me would have her graphing calculator up and on over here all the time, and the Mobi going over here all the time. And so she used both. But she taught AP statistics, and it's very heavily based on correct usage of the graphing calculator. And so she wanted both screens so she could have them both going. I use the graphing calculator that's on my computer when I need it, but she used both. Okay, so this function has a 0 of negative 3. The x-intercept, therefore, would be negative 3, 0. The y-intercept, if I plugged in 0 for x, the y-intercept is 27. Yes, sir?
What's the opposite absolute value of 0?
What is the opposite
Opposite absolute value.
of the absolute value of 0? 0 doesn't have an opposite. It is,
There's no negative.
yeah. What, it's like our fulcrum for the number system. Everything is based around 0. And so it has no opposite. It is that point in the middle. Yes. Alright,
It'd be 0.
thank you. Alright, so the new word for the day is extrema. And extrema just means, basically it represents the extreme values of a function. Our maximum and minimum values. So that's what extrema means. It's the maximum or minimum values of a function. And we have two different types of extrema. We can label them as absolute or relative. Now, we're going to, every absolute is relative. Not every relative is absolute. So we're just going to call them all, no we're not. After this unit, we're going to kind of stick with relative. Whenever they ask you for extrema, they're talking about relative. Right now, we're going to label them as absolute versus relative. So, absolute extrema. That is absolutely the highest or lowest point on a graph. So you see here, first I gave you an example of an absolute value that opens up. So that vertex of the absolute value is the lowest point on that graph. There's not another point lower than that. So that is called an absolute minimum. And I always abbreviate minimum as min. Now the second example I gave you is a parabola that's opening down. And the vertex of this parabola is the highest point on the graph. There's not another point higher than that point. So that is an absolute max. So we would only label it absolute if it's absolutely the highest or the lowest point on the graph of all the points on the graph.
If it's infinity, can it not be absolute?
Infinity is not a point. We can't get there. It's a concept. It's an idea. So infinity is never an answer to a maximum. Now, the second classification is relative, and some teachers and textbooks might use the word local. So if you're Googling some of this later on, you might see it called local. I usually say relative. Relative means in relation to the points that are just around the point, it is higher or lower than all the other points. So when we're looking at a function like this one, this cubic here, do you see this valley down here? That is considered a relative min, the bottom of the valley, because this point is lower than the points just to the left of it and just to the right of it. So that's a relative min. But it's not the lowest point on the graph, is it? Because the graph goes down forever over here. So that's just a relative min. Relative to the points around it, it's the lowest point. And this peak right here, this mountaintop, this is a relative max. Because relative to the points on either side of it, it's higher. So that's considered a relative max. Now, on this next example, somebody asked about this one last period. They said, what if we had two maxes that matched up? So I drew this function, and I said, okay, this is the relative min. And here we have a relative max at the point, let's pretend this is the point 312. And this is the point 612. So these two match up, don't they? So we would say this function has a maximum value of 12. Isn't that the biggest value of the function? Mm-hmm. Yeah. So we have a relative. You could say there's a relative max at the point 312 and a relative max at the point 612. But the maximum value of this function is 12. So did y'all hear me word that two ways? I can say a relative max occurs at the point, or I can say the function has a maximum value of. So in one, I'm giving the point, and in the second, I'm just giving the y value. Right now, I'm okay with the point. By the time you get to calculus and you're finding max and min values, you're just talking about the y value. But I don't want you to know that. Anyway, we could say it occurs at the point or the value is. Okay, so here's our little graph. All right, this is at a valley. This would be considered what? A relative min. So we have a relative min that occurs at the point 1, 2, 3, -1.
Actually, that's kind of like
What about the little point to the left of it?
0.9. Okay.
This is. Okay, and then this one.
Relative.
Relative max.
That's a relative max, and we would say that relative max occurs at the point 1, 1, 2, 3, 4.
What about that little point in the far left?
This
Yep.
one over here?
Yep.
If you look at it, the points on the left of it are lower than it. The points to the right of it are higher than it. So to be a max or a min, both of them have to be higher on either side if it's a min, or both have to be lower on either side if it's a max. This is just a random dot we placed on the graph. It is neither a max nor a min.
It could be
Because on the left side, points are lower. On the right side, points are higher.
Power point.
To be a max or min, look at this point. On the left, they're higher. On the right, they're higher. Therefore, it's a min.
Oh, okay.
On this one, on the left, they're lower. On the right, they're lower. Therefore, it's a max.
Same, like the one on the to the right of that, it wouldn't be it because of the arrow right there.
right.
Oh.
There's.
Okay, that's it for the lesson. Your homework is the front of the worksheet only.